In today's lecture, we're going to go into chapter 4, which is kind of a fun chapter. It just kind of explains a lot of the weirdness and things that are a result of quantum mechanics. But we're going to talk about one of what I think is the sort of most amazing and interesting thing with quantum mechanics, which has to do with what are called Bell's inequalities, which relate to local realism. Um, so Bell's theorem, kind of pretty famous. And just some of my favorite quotes about it. Henry Stapp said that Bell's theorem is the most profound discovery of science, and hopefully today we'll kind of see why he might have been led to say that. Another quote is, put simply, Bell's theorem says that my idea of naive realism is in conflict with the predictions of quantum theory in a way that can be tested in a laboratory in special experiments on pairs of quantum particles. These experiments had been done, quantum theory had been proved right, and naive realism wrong. Um, and you know that if you're not familiar with realism and that might not seem like much, but it really is at the heart of what I think is just so remarkable about quantum mechanics. So Bell's theorem. Bell's theorem essentially deals with correlations between two measurements, right? So say I make a measurement, we'll call that measurement A, you make some measurement, measurement B. If the results of our measurements are correlated, every time I measure something, you get a similar result, or anti-correlated, you get a different result, or those correlations is what Bell's theorem is sort of speaks to, right? And the explanations of correlations essentially in classical thought, in the way we classically explain things, come in sort of two types, right? Let's say the first one is something involved with measurement A influences the result of measurement B, right? So I make my measurement here, and then you make yours, a short time later. Something I did or involved with what was going on in my measurement influence the result of yours, so that every time I do it, your result is going to have the same, that correlation. They're going to be correlated that way. Or another explanation is that what I'm measuring and what you're measuring had some sort of shared past that influenced the result of those measurements, right? So let's just say, pick something simple, like we're both measuring, say, the speed of a ball, or right, or speed of a cart on an air track, right? I measure one, you measure the other, and we both always measure that they're moving at the same speed, right? And that could be explained by, let's say, those carts started together, connected by a spring that pushed them in opposite directions. I measure one, you measure the other. They're always, if they're the same mass, are going to have the same speed, right? So that would be an explanation of that. They shared some past that caused subsequent things to happen, and those results are correlated because of that, right? And if, at least when I think about it, I can't really think of sort of other ways to explain correlations that really exist for sensical reasons. Um, these explanations have sort of things laid into them. One of the big ones, is they're local, right? Measurement A, that sort of influence. Let's say I do something, it's locally influenced. We know signals and things can't propagate faster than the speed of light. So if I make measurement A and you're making measurement B some distance away, if you make your measurement in amount of time that doesn't allow any signal from my measurement to get to yours, they could not have influenced each other. Special relativity tells us nothing can move faster than the speed of light. So the influence of my measurement has to sort of stay locally within however far light could have traveled in the given time between events. Um, Explanation two is local in the sense that that sort of space, locality is propagated through time, right? There's something happened at some point in the past that influenced both things that are being measured, and then that they propagate out, moving sort of point to point through space and time until they're ultimately measured, right? But they're connected causally, locally, I guess is what we're getting at here. There's another concept called realism. Now, this is sort of the belief that objects have a set property whether we know it or not, right? This is, um, the this kind of is one of the problems that Einstein and some of the early people working on quantum mechanics, one of the issues they had with quantum mechanics is they were like, well, it can't be a complete theory, right? They had this idea that, if those measurements are really probabilistic, if I measure a spin 1/2 particle as spin up or down, and I can't, I can only give the probabilities of those, that can't be a complete theory. That particle must have a real state and we just must not know the outcome. We measure 10 spin 1/2 particles, 7 is up, 3 is down. There must be something we don't know, or there must be something incomplete about our thing, because realism kind of says that it has that property whether we know it or not, and a complete theory would be able to explain that property. And one of the things they tried to do that people can say is, well, there's got to be some hidden variable involved with this object that describes that state that we can't really know. And that's realism. What's really cool is Bell's theorem and the experimental sort of proof or violation of Bell's inequalities has shown that neither of these things are true. There are things in the world that behave in a way that these local explanations cannot explain, and that this realism is not true for quantum mechanical objects. And I think that's, when you really think about it, just kooky dukes and insanely interesting. So let's start by just explaining the experiment. Forget how to analyze it or what it's going to prove or show, and let's just explain, one type of a so-called Bell's experiment, and a simplified case that really gets at the heart of what's being done. Let's say you have two spin 1/2 particles that are created in some process and sent in opposite directions. So they go out there. Now we push in two people, Alice and Bob, at each end, opposite ends, each receiving one of these spin 1/2 particles. They both have a Stern-Gerlach analyzer to measure it in. And they agree, they can align it any which direction, but they agree to align it in one of three directions. 0, we'll say that's along the z direction, or 120 degrees or 240 degrees in that plane, right? So, we'll call 0 degrees the A direction, 120 the B direction, and 240 the C direction. But basically, they align it in one of three agreed upon directions, and that's the only way they're going to measure it. Now, they generate one pair of particles, shoot them out. Both of them independently just randomly select one of those three measurements, A, B, or C alignments, and then measure their spin 1/2 particle as spin up or spin down. That's it. They measure a plus if it's spin up the way they measured it, or a down if it's spin down the way they measured it. They don't really care about whether they chose A, B, or C. They just randomly select an alignment and measure and say that was up, that was down. After they've done this several times, they have good statistics in that, they get back together and they say, okay, the first pair, well, I got up and up, I got up and down, and they compare the results from each, spin 1/2 pair of particles they created that they measured, and they look for correlations, in the pairs. How many times did we both measure plus, or how many times did we both, one of us measure up or down, or those sort of things. And that's the experiment. That's the gist of it. So now let's think about how, what would we expect? How could we explain correlations or results in these experiments? Well, classically, or using local naive realism, remember we had those essentially two types of explanations. First one measurement, Alice's measurement, say it's made first, somehow influences Bob's measurement, or vice versa. Or number two, when the particles were created, they were put in some state, and realism says that, whether we know or even can know about the result, that state exists, it's real, and all the measurement outcomes of that spin are known are exist before the measurement is made in that. So those are the only two types of explanation, right? In local realism consistent ones, right? Now, how could we test these types of explanations or possibly remove them as possible explanations? Well, the first one's kind of easy. Just split up Alice and Bob. It's easy in principle, we should say. Alice, you stay way over there. Bob, you stay way over there. Delta X distance apart. And we're going to synchronize your measurements somehow. We're going to have your times synchronized that you measure them to within some small delta t of each other so that, the distance apart you are divided by the delta t, the maximum distance in time between your measurements, is greater than the speed of light. That way, there's no way one of you could influence the other. Nothing can travel faster than the speed of light. Alice's measurement could not have influenced Bob because there's no way anything could have been, that part of the universe could have known the measurement was even made yet. That would violate locality. We'd violate special relativity. So split up Alice and Bob far enough, have their measurements be timed well enough, and that first type of explanation out the window can't explain things. What about the second one? Well, this assumes that when they were generated in that shared past, they had process in the universe gave them some set outcome for those experiments. Whether we know it or not, or whether it's in some hidden variable, though the results of the measurements were known as soon as they were created in that shared past. So how can we test that? That's a testable thing. Well, if we assume the two particles have set outcomes, and again, not that we know what those outcomes would be or that we can predict them, just that they exist. Each particle would have to have some set of instructions or hidden variables or something describing those things once they're generated. So we could look at one particle and say, okay, we know this state exists where if it was measured along A, it would be spin up, B it'd be down, and C it'd be down, say. And you'd be able to write this sort of list of outcomes, one set of outcomes for every particle that's generated, right? And it's essentially, if it's measured along A, it's going to have two possible outcomes, B, two possible outcomes, C, two possible outcomes. So there are actually 2 to the 3 or 8 possible, different sets that each particle could have created when it was first generated, right? That means, 8 times 8, 64 possible combinations of these two types of particles could be created, right? So given that, we can say, okay, let's look at, those possible combinations, what the probabilities of measurements outcomes would be, and you could determine what those correlations would look like, right? If we randomly select an A, B, and C between Alice and Bob, Bob would have measured this, you would have measured that, and you could actually just analyze this and get those correlations and predict, sort of the range of possible correlations Alice and Bob could have, right? Then you perform all those measurements and you see if you're within that range, right? And if you are, local realism can still explain these types of measurements. If you're not, you have violated that. And we have put like hardly any assumptions into these explanations. All we've said is, essentially things are local. Nothing can travel faster than the speed of light, and that realism is a thing, and that these particles have these known outcomes, whether they are knowable by us or not, just that they exist beforehand. So it is testable. Now, what we're going to do in this case is we're going to do a simplified sort of version of this experiment a bit more, and we're going to say that these particles, when they're generated, are conserving angular momentum. And they're generated, I think the book uses the example of generated through some decay so that the spins have to be opposite. But essentially, we're going to say that angular momentum is conserved when they're generated, so that if you measure one particle along a given axis and the other particle along the same axis, their spins would have to be opposite, right? So if Alice and Bob both measure along axis A, and one measures an up, the other one must measure down, right? So that means we still have 2 to the 3 possible sets for a given particle, but having the one set sort of determines what the other set would be. So this is a possible sort of sets that each particle could have. Particle 1 all up means particle 2 would be all down, and vice, and permutations of the different options there. There's 8 different possible ways of generating particles in this experiment. Um, so we can now calculate what the probability of those different results are, right? And we can do that to develop, to see what sort of correlations we can get. And the way we'd calculate that probability is this, right? The total probability of measuring, let's just look at 2 types of correlations. What are the probability that Alice and Bob have the same measurement result? They both measure up or they both measure down. So they measure the same spin versus measuring different spins, one up, one down. Well, the probability that they're going to measure the same type of spin is the probability that the particle pairs were produced in the first sort of set of instructions, that n1 there, divided by n total. So that's going to give you the percent of the particles that had that set of instructions. And then if given that set of instructions, what's the probability that they got the same measurement outcome? Likewise, for 2, you add those all up and you get sort of your expectation value or the probability that they're going to have the same, measure the same spin component, right? If we look at this, what's the probability that the first set of instructions results in them measuring the same thing? And that's 0. Particle 1, all of them result in spin up. Particle 2, all of them result in spin down. There's no way you can measure them the same, so that probability is 0. For 2, if particle 1 is measured along A, it's spin up, and it will have, if particle 2 is measured along C, that's one way of measuring spin up. If particle 1's in B and particle 2's in C, that's another way they measure the same. The only other ways are if particle 1's measured along C and particle 2 is along A or B. That's 4 different ways we can measure the same spin value in between Alice and Bob. Out of the 9 total possible ways we can measure them. So that's 4/9 of the time. For every 4/9 of the time the particles are generated in sort of the pairing 2, we have that probability. If we go through these that same sort of way, we notice 3 sets, 2, 3, 4, 5, 6, and 7 all have that same 4/9 probability of the measurement results being the same. Right, and if we look at particle, setup 8, those have 0 probability. Right, so those are all the probabilities of measuring the same result for each individual set of instructions. If we take the probability that those set of instructions were produced, we end up with this, right? 0 for the probability for the first and last sets, and all the individual n2 through 7 sets have a 4/9 probability, so you can just factor out that 4/9, and we get the total probability that these things are going to be measured the same. And this is true whether they're all produced in the n2 state area setup or in the n7 setup. That works for everything. But what does this mean? This means the highest possible probability we can have is if all of them are in that 2 through 7, one of those 2 through 7 states, right? And that would make the probability 4/9. So 4/9 of the time we have these matching spin measurement results or less, according to these explanations. You can do the same sort of analysis or just 1 minus that to see the probability that they're different. And you get that that's going to be greater than or equal to 5/9, that they're going to be measured with different spins, right? So hopefully you followed that, but this is a testable thing, right? Alice and Bob go and perform this measurement, randomly select their axes, measure it a bunch of times. If they get results, if you've measured it enough, you've got a small enough uncertainty on what the actual probabilities are, you get what the probabilities for being the same and different were. Is it within that range or not? And if it is within that range, then local realism can explain these results. It is possible to make an explanation for that. If not, though, you have to throw all this out. You cannot explain it with those types of explanations. So what does quantum mechanics have to say about this stuff? Well, let's look at two spin one half particles. We know first particle, called psi1, second particle, psi2, can both be written as linear combinations of spin up and spin down in the z bases, alpha, beta, gamma, eta being those complex coefficients in that linear expansion. Well, the two particle state in quantum mechanics is defined by psi1 tensor product with psi2. Now, tensor products are going to be beyond the scope of this course and all that. We're not going to get into the formal math of doing that, but substituting what we know our state functions are in Braun-Ket notation, in this Dirac notation, it's actually kind of straightforward to see how it works out, right? You essentially would do this almost like your standard, FOIL algebra, right? You take the plus and the plus, create one two-state ket for that with their coefficients multiplied, and likewise through all the others, right? All of those coefficients are just two complex numbers multiplied to each other, which we can replace with a single complex number. But that two particle spin one half state and a general two spin one half particle state can be described like this, as a linear combination of a set of four basis vectors, the plus plus or up up state, the up down state, the down up state, and the down down state, with A, B, C, and D complex numbers. So just like we've done in our simple two-dimensional Hilbert space for a single spin one half particle, we're in a bigger space now. We have a four-dimensional space with A, B, C, and D complex numbers on each of our basis vectors, right? So we can sort of go through the math of this in the formal quantum mechanics if you're willing to accept that. But everything else is the same. Those basis states are orthogonal and they're normal. So all the sort of Dirac math that we've done previously will work for these as well. In our experiment, remember, we've had that angular momentum conservation thing that showed that the spins had to be opposite for each in a given measurement. Turns out, if you go through all that, it's in what's called a singlet state. So the state of the two spin states in our measurement are actually this, a spin up down minus down up all over root 2. So it's normalized. So those are the state of that's the state of our two particle spin system, two spin one half particle system. We can now ask, well, what does quantum mechanics have to say about the probability of measuring up up, say, if Alice's detector is aligned at an angle theta away from Bob's, right? So we'll just define the z direction as however Bob aligns his Stern-Gerlach measurement. Alice can either be aligned with it 120 degrees, 240 degrees away. Well, that, postulate 4 that we've been using is just the projection of our state onto the measurement outcome, all squared, that measurement outcome being a spin up in the n direction and a spin up in the z direction for Bob. We know that a spin up, a single particle spin up in the n direction state can be written like this in that z direction. So if we do that same sort of tensor product previously, we end up with this being our sort of measured state written in the same bases, that sort of z bases for the two particle system from the previous slide, right? So all we have to do now are these inner products, right? And just like before, the inner products of a Braun and a Ket that are different are 0, and an inner product of a Braun and a Ket that are the same is 1. So if we do all that, we end up with the probability of measuring a spin up and a spin up when their Alice is at, in some direction n relative to Bob's detector is 1/2 sine squared theta over 2, whatever that theta angle between their detector alignment is. Likewise, we can go and look at the spin down correlation. So that gives us the same thing actually, 1/2 sine squared theta over 2. So we have the two probabilities of measuring the same result, up, or down. Adding them together, it's sine squared theta over 2. And 1 minus that, or go through all that analysis again. For those cases, you end up with cosine squared theta over 2 for being the probability of measuring them different if they're aligned at some theta, if Alice and Bob's detector are off at some theta. With this, we are able now to determine the correlations like we did in the classical sort of explanations we were going through, right? If we know that the same probability, the same and the different are those depending on what angle, and we assume, or we don't assume, we have Alice and Bob just randomly select which alignment they choose, theta 0, theta 1, there's 1/3 of the time they're going to be measured at the same angle. 1/3 of the time they're going to be 120 degrees off, and 1/3 of the time they're going to be 240 degrees off. So we just plug in those values into our probabilities that they're the same times 1/3, because 1/3 of our values will be that, add them all up, and that's what we get. So doing that, 0 for the first one, 3/4 for the second, 3/4 for the third, add them all up. That means 1/2 of the time we would expect Alice and Bob to measure the same result. Likewise, 1 minus that, 1/2 of the time they would measure it differently, right? And so we have those two situations. If we look at those local realism explanations, we know that the probability of measuring the same result between Alice and Bob has to be less than 4/9. Maximum it can be is 4/9. The probability of measuring different has to be greater than 5/9. Quantum mechanics allows violations of those inequalities. So those are there's several examples of these, but this is sort of a simplest case of Bell's inequality. And quantum mechanics predicts that you can violate those inequalities and show that local realism doesn't hold and can't explain this. And that's the amazing thing about this. Experiments have been done that have shown this, have violated Bell's inequality and shown that the universe cannot be explained by local realism, right? These have been done, it was actually the early 80s, I think, is when some of the first measurements were done. But they've continued up, and have been ongoing and continually showing violations of Bell's inequality. But even very recently, groups have been making, Bell's violation measurements. And the reason there's still a lot of interest in this, well, one of the reasons, there's tons, is because there are loopholes in these explanations, right? So there are lots of different ways people try to poke holes in this idea, and skeptics try to argue that no, we can't get rid of realism or locality because of, such and such reason. And these are generally called, loopholes. One of the big ones is this sort of detection, or what they call fair sampling loophole, right? And the idea is, a lot of these measurements, the first ones especially, were done using photons, entangled photons sent in opposite directions and then detected. Well, when you're making single photon detectors, that's really hard, right? So there's some missed counts, right? So you might create a pair of photons, but only one detector actually managed to measure it. So you'd throw that one away, and you'd only look at a subset of all the pairs that were created. And an argument can be made that, even though, no experimenter meant to skip samples and it was just sort of totally random, you can make an argument that that doesn't mean that it was a fair sampling of all of those entangled photon pairs, right? Maybe the violation of Bell's inequality wasn't because that the actual physics in these systems violated Bell's inequality, but it was because you were, all the ones that were missed happened to be the ones that weren't correlated in the way you'd expect, and you were just sampling a biased sample, unintentionally through, faults in your detectors, but that wasn't it. So that was one of the big loopholes. And then people would close that loophole, but often there'd be a different loophole that was the locality loophole, right? Again, if you want to send a single photon one way and another one the other way, the farther they go, the harder it is going to be for those photons to make it to where they're going to be measured and all that. So synchronizing measurements and separating them at a level that is isolating them, having the distance divided by the time between measurements less than the speed of light or greater than the speed of light was really difficult. So a lot of, these first early Bell's violations weren't actually local, right? Now, I think, again, it's hard to argue what sort of signal could have possibly passed between detectors or anything like that. But the fact that theoretically there could have been some signal sent, even though, say, you put one detector in a Faraday cage that's blocking out all the EM radiation and all those things, technically a signal could have made it there, whether you know what that signal is or not, and influence the measurement. So that was a loophole, right? There are still these sort of loopholes in a lot of these tests. You put them closer together, and you might be able to beat the sampling loophole. Separate them, and you beat the locality one. But it was hard to do both. Um, there are other loopholes too. One of the requirements in this was that Alice and Bob are actually randomly selecting their alignments and that. And people have even tried to argue, well, if they, even though they don't know it, if they were predetermined selections in their heads somehow, that could be a loophole. And I don't think many people take that one as seriously. But the big two loopholes were here. And in 2015, some people called it the year of the loophole-free Bell test. I think there were three different groups that measured it, but the one shown here used electron spins in diamond defects to do it. They closed both the locality and the detection loopholes in single measurements, right? So there really was, there's no, in my view, no reasonable way of trying to argue against the fact that nature really isn't local. Local realism can't explain these quantum phenomena. What this group from Delft actually did in this Henson paper, they set up a thing here that sent two photons to their diamonds, measured the spins of the diamonds in one measurement set up at A on one side of the Delft campus, one at setup B on the other side, just over a kilometer away, and measured their correlations. And they were able to synchronize the measurements in a short enough time that no signal of light could have traveled between A and B in time to influence those measurements. And their detection fidelity was high enough that they sampled enough that their confidence in their correlations didn't allow for that sort of loophole. So that's it. I think this spooky action at a distance that Einstein had issues with, and when he first proposed the EPR paradox, turns out that that actually is what happens, and it's not that quantum mechanics is incomplete. It's that the universe is non-local and kind of random. So yeah, really kind of crazy ways of thinking about things that experimentally have shown this with Bell's inequalities and Bell tests. Uh, right. This is a bit of a long video. Hopefully you enjoyed it. I will see you in our synchronous sessions.